Now we'll discuss about the vehicle movement. The movement behavior of a vehicle along its moving direction is completely determined by all the forces acting on its direction. So when vehicle is moving, different forces are acting, and these forces will decide basically the movement of the vehicle. The tractive effort Ft in the contact area between the tires of the driven wheels and the road surface propels the vehicle forward. It is produced by the power plant torque, that is nothing but the IC engine, or it will be the electric drive which give the required torque and transferred through the transmission and final drive to the wheels. While the vehicle is moving, there is resistance that tries to stop its movement. It opposes the movement. So resistances offering are responsible to stop the vehicle, and we have to give and or we have to drive the vehicle against these resistance or opposing forces. The resistance usually includes tire rolling resistance, aerodynamic drag, and of hill resistance when vehicle is moving on a steep road with positive slope. The acceleration of the vehicle depends on power delivered by the propulsion unit, that is the power delivered by the engine or power delivered by the motor, road conditions, whether it is a smooth road, whether it is a rough road, whether it is a tar road, or it is a concrete road. So this will decide the vehicle acceleration, aerodynamics of the vehicle, and composite mass of the vehicle. So these all are responsible for the acceleration of the vehicle. According to the Newton's second law, the vehicle acceleration can be written as, considering force equals mass into acceleration. This acceleration is force divided by mass. So we can represent this acceleration in terms of rate of change of velocity with reference to time, that is dv by dt is equal to the total tractive effort of the vehicle that is given by the engine minus the total resistance to the vehicle. So this is the difference, and net force will act on the vehicle to accelerate it divided by mass of the vehicle into a factor delta. That delta is mass factor that equivalently converts the rotating inertia of rotating components into translational mass. So we have to get it into translational mass. So that conversion is done by a factor delta. Now, if you see this diagram, into this, we can see the various forces acting on the vehicle. So the vehicle is moving in this direction, so velocity is shown. Now the forces, opposite forces are here. Basically, it is the aerodynamic opposing force. Then we can see weight of the vehicle, mg. So it's two components, mg sin alpha and component of the mg cos alpha. So one is downward and one is opposing to the velocity or opposing to the vehicle in the opposite direction. Also, we can see there is a resistance, that is the rolling resistance, and rolling resistance torque will be there for the front wheel and for the rear wheel also. So it is also in the opposite direction. So these forces are there. So you can see there are aerodynamic drag FW. There is rolling resistance at two wheels TRF and TRR. That is front and rear wheel rolling resistance, and hill climbing resistance, that is mass into gravity into this component sin alpha mg sin alpha. So these are the three opposing main forces, and after subtracting these three forces from the net tractive force, from the tractive force we can get the net force which is acting on the vehicle to accelerate it. The first is the rolling resistance, can be discussed in detail here. The rolling resistance of tires on hard surface is primarily caused by the hysteresis in the tire material. So this resistance is because of the rolling of the tire, and which is the rubber material. So mostly it is related to the hysteresis phenomenon. We can see this figure which shows a tire and it is in the standstill position. It is not rotating, or there is no any weight, and it is in the there is a weight but it is in the standstill position, and force P acting at the center. So because of that force is acting. The pressure in the contact area between the tire and ground, so pressure between the contact area, tire and ground, is distributed symmetrically to the central line. So you can see whatever this force P which is acting here, it is distributed over the surface equally. You can see this, that is about this central line, and resultant reaction force Pz is aligned to P. So resultant reaction force which is balancing this force P which is from this resultant, and it is the Pz. Z is the deformation of the tire because of the weight or because of the force acting on it. So these things are under the standstill condition. Now if you see, there is a deformation which is the Z here is shown. So this is the deformation because the tire has to be likewise naturally, but because of the rubber material and force it will be having this deformation, so the tire will be like this. So this shows this much deformation or contact surface. Now if we see this hysteresis into the rubber material or tire, so it is shown into this force acting on this axis and deformation Z on this x-axis. Due to hysteresis, the deformation of rubber material, the load at loading is larger than that unloading at the same deformation Z. So you can see during loading and during unloading, these forces are different. So if you see this one particular point, deformation point, and if you see the force here, the loading, we can see the loading or force here is different, and another point, loading and unloading point, you can see P2, it is now different. So it has to follow the same path during the loading and unloading, but the another part is not the same, it will take the different path. So this is the hysteresis phenomenon or hysteresis loop, and this will show that the loadings are different the forces are different, loading, unloading, and loading. Further, it can be seen in detail when the tire is rolling, as shown in figure. So here the tire is rolling now. Earlier it was standstill, so the forces were equally distributed around this central point, but now it is different. So we'll discuss this phenomenon when the tire is moving. It can be seen that the leading half of the central area is loading. So leading portion, if it is moving into this direction, so this is the leading portion, and the trailing half is unloading. So this portion is the trailing half. So this is unloading, because when tire is moving, it applies the force, so it is a loading. When it has left or it is traveling, so this portion will now come and its loading is removed, so unloading portion. So this half is loading and this half is unloading portion. Now hysteresis causes an asymmetric distribution of the ground reaction force. Because of this hysteresis, the force during loading and force during unloading is different. So because of this, there is asymmetric distribution of ground reaction forces. So reaction forces during loading are different and reaction forces during unloading are different. That's why there is unequal distribution. So the pressure in the leading half of the contact area is larger. You can see the pressure magnitude is larger here, pressure is larger than that of the trailing half. So the portion which is just getting detached or getting removed because of this rolling, it is having the lesser force, that is lesser pressure. This results in the ground reaction force shifting forward. So you can see the ground reaction force, this P, which was earlier at this exactly at the opposing and at the center point, it has now shifted because during loading and unloading, the pressure is different. The pressure is more at this portion as compared to this up portion. So if we take the resultant or average, it will shift here in the at this portion. So this is the some distance here. Now if you see in the earlier, it was exactly at the opposing ground reaction or this pressure, but now it has shifted somewhat in this portion. So this is because of the loaded and it is also rolling. So this is the hysteresis, and because of that the resultant force is different now, which is the reaction force, and shifted in the forward direction. This results in the ground reaction force shifting forward direction. This forwardly shifted ground reaction force with the normal load acting on the wheel centers creates a moment which opposes the rolling of the wheel. So we can see this. One force is acting in this direction, another force is acting in this direction. And if we see the effect of this, so one force is acting here, which is this. Another is not acting exactly in opposite direction, equal and opposite, but it is now acting on this slightly forwarded position. So resultant will be just in this direction. So it is in the opposing. So you can see, or you can check that one force is acting on this portion, one is acting on this portion. So there will be a twisting, or it can be have some, because rolling is in this direction and these two forces are creating movement in this direction. So this is how the hysteresis is coming into picture, and it creates a opposing force to the rolling direction, opposes the rolling of the wheel, and this is nothing but the rolling resistance. It is because of the rolling itself create opposition. Now this is shown on the hard surface. The rolling resistance phenomenon is shown on hard surface. On soft surface, we can see here the rolling resistance is primarily caused by deformation of the ground surface. So ground surface will also have some deformation. So the ground itself will deform. Here the tire has some deformation on the hard surface. Tire has deformation, but here because of the soft surface and because of the weight or the pressure, it will have the deformation, and this deformation will further create the hysteresis shifting of this reaction force component here larger, more than the hard surface. The ground reaction force almost completely shift the leading half. So most of the leading half is shifted now. Some portion was here in the trailing half, but now you can see most almost it is shifted, and then nothing is there on the trailing half. It is shifted into the front half. So the twisting moment or opposing moment will be larger. So it is, we see that it is difficult or more torque is required, more force is required from the engine or from the motor to run the vehicle on the soft surface. Here we can see some questions. The moment produced by the forward shift of the resultant ground resistance force is called rolling resistance moment. And we can express this as TR is equal to P into A. This is the deformation of the tire. We can indicate this with Z also. If the notation is taken as a Z for the deformation, so it can be PZ if it is taken earlier. So Z can be taken as the deformation of the tire, or A is the deformation, then it will be PA. So TR is the rolling resistance in Newton meter. P is normal load acting on the center of the rolling wheel. M is the mass of the vehicle in kg. G is the acceleration constant. Z is the deformation of the tire. So with this, we can write the expressions. To keep the wheel rolling, a force F acting on the center of the wheel is required to balance the rolling resistance moment. So this force can be expressed as F is equal to this torque dr divided by Rd, where R is the effect, Rd is the effective called as a dynamic radius of the tire. In the moving condition, the radius of the tire will change, and that is the dynamic radius considering the deformations, and it can be written as TR divided by RD, and that is nothing but PZ if deformation is taken as Z, PZ divided by RD. Now this Z divided by RD, that is the dynamic radius of the wheel, we can call as rolling resistance coefficient, and here it can be written this Z upon RD can be represented as FR, which is Z upon RD. So it is integrated by FR, and that is the rolling resistance coefficient. The rolling resistance moment can be equally replaced by a horizontal force acting on the wheel center in the opposite moment direction of the wheel. So this equivalence force is called rolling resistance, and we can write this FR rolling resistance is nothing but P into FR. So P is the normal load acting on the center of the rolling wheel, and FR is the rolling resistance coefficient. So we have seen that rolling resistance coefficient will depend on the deformation of the tire and the dynamic radius of the wheel. When a wheel is operated on a slope road, the normal load P should be replaced by the component that is perpendicular to the road surface. So if it is not on the normal, there is a slope, then we have to consider this equivalent uh, load with respect to the slope, and that is nothing but Fr is equal to rolling resistance is equal to P into Fr into cos of this alpha component, where alpha is the road angle. So we have to consider the road angle, and cosine of that will give the equivalent rolling resistance parameter. The rolling resistance coefficient Fr is a function of the tire material, tire structure, tire temperature, tire inflation pressure, tire geometry, road roughness, road material, and presence or absence of liquid on the road. So various conditions will decide the rolling resistance coefficient. For fuel saving in recent years, low resistance tires for passenger cars have been developed. Their rolling resistance of coefficient is less than 0.01. Here we can see some rolling resistance coefficient for car tires on a concrete or asphalt road. It is 0.013. On rolled graved road, it is 0.02. Tar macadam road, it is 0.25. Unpaved road, it is 0.05. On field, if we see the rolling resistance coefficient, it is 0.1 to 0.35. Truck tire on a concrete or asphalt road, it is 0.006 to 0.01. On iron rail, it is very less, 0.001 to 0.002. So rolling resistance examples coefficients are shown. Based on the experimental rules, many empirical formulas have been developed to calculate the rolling resistance. For example, the rolling resistance coefficient of passenger car on a concrete road is given by this equation. Fr is equal to F0 plus Fs into V by 100 whole to the power 2.5. So V is the vehicle speed in kilometer per hour. F0 and Fs depend on inflation pressure of the tire. In vehicle performance calculation, for the most common range of inflation pressure, the following equations can be used for passenger car on concrete road. Fr is equal to 0.01 into 1 plus V by 160. The equation predicts the values of Fr with acceptable accuracy for speeds up to 128 km per hour. This is the summary. This is about the rolling resistance, which is one of the important opposing force to the net tractive force.